Hi, everybody. My name's Paul Jensen. I'm the Director of Technology at Aerospike. And what I'm going to present here is a case study in how we were able to actually make use of the 800 series and ADQ to get some pretty impressive performance boosts. I've divided this presentation into 3 parts on 3 slides. First, I'm going to tell you a little bit about Aerospike. Then I'm going to tell you a little bit about what we did to enable it with ADQ. And finally, I'm going to show you the numbers we got. So this is kind of a busy diagram. It's showing Aerospike being used in a lot of different contexts on the edge as systems of record. But historically, Aerospike started out in a very narrow case of it's a NoSQL database that supports real-time and scale out. Those were our original customers were all in ad tech. So the key characteristics that we developed this, or the applications we needed to support, was being able to scale out to massive amounts of data, but be able to return results in milliseconds. In ad tech, if you miss that, you've lost, you're losing revenue. So at a very high level, the way this is implemented is we had to make a lot of assumptions to make this work, because simultaneously hitting both scale and real-time constraints is not easy. It's a key value store. It does have complex data types. It does not have transactions. So everything, it's record-oriented, and there's atomicity with it at the record level. But there's no concept of multi-record transactions. And one of the corollaries to that is we tend to have lots of little chunks of requests from our clients to process. The scalability, it's server-based, and those servers are in clusters. It's shared nothing. Probably the hardest thing about this is that you can scale up and down, and they're auto-balancing. They are you can add nodes, you can take nodes. Nodes break. It can survive partitions, and that really is the key to scaling, to being able to support really large data sets. It's a client-server architecture, so the clients run in separate processes over the networks, making these record-level CRUD requests. One key thing is that there's no master-slave that some database architectures have. The servers are all essentially peers, and the clients know where they know which servers to talk to. There's no proxying. It's basically it's based on a key hash. So what this gives you is very high throughput, over 1 million transactions per second, a lot more in this case. Latency under a millisecond. Again, the exact numbers depend on the application area, but that's pretty typical. Very reliable, and that's not a typo. It really does scale. Some of our largest customers have clusters with over 100 nodes in them. So. And then the last thing, I said we started with ad tech. From there to things like fraud detection, it's pretty natural. More recently, we added strong consistency in the cap sense, and that that's what allows us to be used as systems of record. We can pretty much guarantee that you will be able to, you're not going to get stale reads or dirty reads. Okay, so that's what Aerospike is. As far as why we wanted ADQ, we're very highly motivated for that because we tend to be used in very high performance settings, but really maybe the key thing is the requirement that remember, we're real time, and real time translates into low latency. So one of our interests in, and you'll see this when we get to the results, increases in throughput are nice, but in a lot of these applications, you live or die based on latency because the SLAs are based on that. And if you're not hitting your SLAs, over provisioning is incredibly painful. It usually just destroys the economics, and you can't do it. So the other thing is we realized that the way that our server was structured, it was actually, it fits in very nicely with ADQ. So we didn't have to contemplate like completely rewriting the servers to take advantage of it. And I would say, in fact, in general, I'm sure there's applications out there that have traffic characteristics that just naturally fall into being able to use ADQ without any code modifications. So the key things is the data. I mentioned we basically distribute the data based on it's a RIPE-MD 160 hash, and we use some of the bits to partition the data in 4096 partitions that are smeared over the cluster nodes, and so the clients know where to send the data, and these requests tend to be fairly small. So there's lots of requests coming from lots of clients, and to take advantage of that, the server's already very heavily multi-threaded, and a key thing is that when a request comes in, it's assigned a transaction thread, and that will really carry it all the way through. We already, so one of the key things is that we're already doing is trying to get very good cache behavior because in these modern, on a modern system, it's sort of a double-edged sword. You have all these different levels of caches, but if you have bad behavior, it's like watching a pinball machine. And that again, that kills us on the latency. We were using something called CPU pinning, and essentially what we were trying to do was use CPU affinity to make sure that a request, once it came in, would be handled on a particular CPU. And our implementation strategy for ADQ is we just kind of wanted to extend that. And the particular way we wanted to extend it was to have not just application level processing, but all the driver processing that happens when the request comes in to all be handled for a given request from a client, have that all handled on the same CPU core. Essentially, the biggest part of what we did was we changed our we took the framework that we had for CPU pinning, and instead we extended it to ADQ, and we did that by, you saw in the earlier slide, NAPI ID is kind of the hook that we were able to use that to pretty much guarantee that a particular queue will be tied to a particular core, and the top half, bottom half, ISR, user land, all that processing we want to go on in one core. This works for us because, again, we have no special priority classes for requests. In fact, the traffic class definition was just to distribute evenly the requests over the cores in the system. So one last thing is on multi-socket systems, we actually run for each socket or each NUMA core, we run a separate instance of the Aerospike server, and that actually has advantages that further helps the cache coherency. So let's see, I want to keep us on track. So first thing, this is the results. I'll start with the throughput. We got very impressive numbers. So the CPU pinning we were doing, we were getting 8.6 million transactions, and that went up over 75%. To generate these numbers, we have a test harness. We had, and the key thing here is that we were really trying to make sure there were no bottlenecks that were holding back the network. We wanted to see how hard the network could work. So in this case, we had we had one server. It had 2 cards. We had 200 gig 800 series cards. We had 6 clients. Each of those, I believe, had 40 gig cards. They were all plugged into a switch. We were running 3 instances on each client of a benchmark that generated massive amounts of, in this case, they were read requests 100% because we just wanted to, again, we wanted to really hit the network as hard as we could. And so these numbers, they're pretty impressive, but this is actually not what is more significant. This latency diagram it really kind of tells the whole story of why we are excited about ADQ. So what this diagram, this gets to the question with how do you actually measure latency? When we ran this benchmark, we had millions of transactions. We bucket them. These are basically counting up 40 microseconds at a time. And you can see that with the orange line, which is the baseline case, we have a lot of tail latency. It's very sprawly, and this translates into being hard to hit your SLAs. So with the ADQ enabled, you see this really dives down. So almost all the latencies are pushed down towards the lower end. We have a figure of merit for that called P99, and that's essentially, you can think of it as sort of the latency value, the bucket where 99% of the requests took less time than that. And you can see using the P99 definition, we went from 600 microseconds of latency down to 320. And
Paul, I got a question. So obviously, yeah. I think the performance impacts are pretty sizable here. I'm just curious. You guys obviously had to rewrite or retool your application to take advantage of the ADQ on the 800 series, right? So I'm just curious how long that took for you guys.
There's 2 answers to that question. Yeah. So I'll give you the slick answer, which is how many lines of code did we have to change? Less than 12.
Oh.
So that was very, because because essentially what we had to do was take advantage of that NAPI ID. That's the glue that ties all of this together. So what's hard? Hard is defining the traffic classes. You do that up front, and you don't do that inside the application at all. Aerospike's a Linux implementation. They are TC and ftool commands that you use to define the traffic classes, and it's just the nature of the beast. If you get it wrong, you will lose performance, and it's work to figure out what you got wrong. It's not necessarily going to tell you, do you really want to do this, Captain? So that's one part of it. So the other part is you just have to, we were working closely with Intel, and that helped a lot. It took us a couple of months to, we saw a boost right away, but the hard part was knowing when we had really squeezed the lemon dry and there was nothing left. That took several months, and I don't know how you want to measure. There was startup. We were using new silicon. It took a couple of months though, and before we finally got this really pretty impressive number. That one really surprised us. So a lot of tuning, a lot of testing, a lot of very careful keeping track of every little detail of what you're doing, paying attention to your scripts, monitoring your system.
Yeah, I think some of that's teething, right? Getting used to the whole deployment of the whole thing, and then there is, admittedly, I'll fully admit it, there's a recipe that you have to figure out that's specific to your application that has to do with configuration and stuff. So we're trying to help provide the set of things that work right up front. But at least we have all the knobs in front of you, as opposed to you having to go off and find all the knobs and then figure out how to turn them.
Yeah, so my advice to any developer is the first thing you have to know your app. You have to really understand the structure of the networking structure, because that's going to show you where you have inefficiencies to exploit. And we probably had a little bit easier time because of the nature of the traffic we were handling, but it's a good exercise. You'll know your app better after you've finished than when you started. So.
Thanks.
So thanks.
Yeah, thank you, Paul.